Hello and welcome back to another episode of Getting into Good Oxide. Welcome back, Sydney.
Hello, Sebastian.
And it's good to have you because I didn't do any work and we should probably do this together. Clean up the mess we made yesterday, or I made yesterday, with a little bit of refactoring here in lookup prefix. You already had some intuition last time, and yeah, please guide me through what you would think we can be doing here.
Yeah, it's overall it's not so messy, I think, but yeah, there is some literal duplication going on, right? I mean, the stuff inside the match statement, we really much just copy paste it over.
Yes.
And yeah, maybe there's a way that we can combine this into one loop, maybe, and just have this in one place.
Yes, let's try. So first thing I would probably try is to just let IntelliJ do all the work. Let's see how good the proposition is. Prefix, candidate, index lookup. Ah yeah, it puts the index lookup there. What happens if I do this? Lookup result, whatever. Let's see what happens if I do this. Ah yeah, see. So that's more like it. I can probably also change the order here, can I? Yeah, okay. Lookup result first, then the candidate, and we get, look, it can't determine what we get because of the continue stuff and everything, but it's okay. Let's give it a name and see how we can refactor this. Candidate, check candidate maybe.
Yeah.
Something. Names are easy to change. And on this side, we have to do something. Like we have to either continue or return.
I mean, we only have two outcomes, right? It's either ambiguous or continue.
True.
So maybe it's enough to just return a bool or an option.
Yeah, the continue happens automatically. So it's more like if this says it's unhappy, then return okay, some error, like that. And why is this now colored like it is? Is this a bug? Unreachable code. Okay. I don't know why it's unreachable. Ah, this is why. Because of this. This means the function never returns.
Oh, okay.
You can do this from main loops and such things. But if you change this to bool, it should tell us that we can now return. So here we return true, right? And in the other case, we return false. Or wait, what did I do here?
I think it's the other way around.
Yeah. False. False is bad. False, true, false, assign, and true. Okay. That could be it. So I'm not usually a fan of having these functions being part of me instead, part of the type. So that you have to call it through self. It's amazing that I say I don't want this to be part of me. It's like I self-identify with that type. That's how I code, you know, I must feel it.
You're really in it.
I'm really in it, literally. It's me. That's me. So we can just move this here and declare and define a function inside of another method. Why not? And then we can call it like this. And that's the thing you will typically see, by the way, that if I refactor this into little methods that I just do it like this.
Mm-hmm.
So that I keep the functions hidden and don't pollute other namespaces with functions that are only utilities for use in one particular context. Running the tests. Oh, right. This is now. Okay. Does this need to be? Can I do this?
What?
I see your face. That tells a
It's
story.
already a reference, right? I mean,
what happened? Why did that work at all? Man, that's a cool one.
yeah, you'll have to explain this.
Actually, I think from our previous sessions, you actually know the answer. You know the answer. Okay, let's go back to the problem. Use of moved value. Value moved here. Let me try to use it again. Why does the value move in the first place? I mean, I move it into a tuple, right? This is now in the tuple, and then I match on the tuple. And because this is not, right, I don't want to say too much, but this is now a mutable reference to an option. And what are these doing or not doing? Doesn't matter that it's an option, by the way. It's a mutable reference, so what can or can't they do?
I mean, from my perspective, it's a reference, right? So if you use it here as a reference, I don't understand why it moves in the first place.
But that's the thing. Mutable references always move. And immutable ones, they are copy. But mutable ones are not. Because mutable ones, we don't want to accidentally copy them. Because then you have aliasing. You have two of these pointing to the same memory location, which is supposed to be writable, which is invalid. So they must be moved.
Which is not allowed.
Yes.
Okay.
And now the question, why does this work? Yeah.
Well, because you dereference it, so you get the actual value,
Yes.
and then you create a reference to it again.
Yes, but only a read-only reference.
Mm-hmm.
So this is how I say, okay, in here I want to do read-only, access only, which is true, right? It's read, 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 read. And down here, fortunately, Rust is smart enough to see, because this is still a reference. This is a read-only reference to the content of the option. So even though this is none and you say, well, this is nothing, why would this be a problem? Well, it's still something. It's a variant of that option at that memory location, which is now immutable here. But fortunately, Rust is smart enough to see, you don't actually use this anymore. After the match, it goes away. So now I can have access to my original mutable candidate again and assign to it. And this is how it works. So basically just, it makes sense, right? Like if I have a mutable reference, I can temporarily obtain a read-only reference to the value because it's a downgrade essentially. I can use that read-only thing, copy it around, and if I stop using all the copies of the read-only thing, I can start writing to it again. And Rust is pretty good in detecting when that is happening. So yeah.
That's pretty cool, yeah.
Let me try something. Oh yeah. So look what I did now. I now assigned none, which is still a read-only reference to none. I assigned this to a name. So X is now bound, or has now bound the variant none of candidate. And if I were to, let's see, I don't know, can I do something with this? Can I just print this? And now you see what happens, right? Now I cross path here. I keep a read-only reference alive for after writing to candidate, and this might invalidate this one, hence not allowed. But if I do it here, it's fine because I don't read after I write through.
Okay, so instead of dropping those values at the end of the closure or at the end of the scope, it kind of knows to do it beforehand.
Yes. Yes. It does that for me, right? It automatically says, you're not reading. It does the right thing essentially. Because still technically, yeah, I still have access to it now, but I don't use it. It's smart enough to detect that. Only when you actually use it, it will bark at you. And that's really nice. Cool. And now we only have to put that right here. Let me get a lookup result. Because then I can just copy paste this. Okay. Okay. Technically, we have more lines of code now, right? Or do we? Do we have more or not? Maybe less.
Should be less, right?
"21 insertions, 17 deletions." There you go. I actually added code by trying to remove it. But I think it's okay. Because of that logic duplication, you don't want to have missed bugs there and then have to fix them twice. Of course, there are no bugs because of the way this is done. So it's safe.
And just out of curiosity, like trying to combine the two loops into one loop, because for some reason that would have been my first approach. But of course, that's a lot harder in Rust because you can't easily combine the types, right? I mean, you would have to use traits probably or something like that to say both of those have a lookup prefix function.
Yes, exactly. That's true. I mean, technically they have a lookup prefix function both, and that's the same thing, but they're different types, and you would have to put them behind a trait, and then you have to locate them. Or you can potentially put, I mean, you can do it like this. You can just put the object database into the index here, like this. What's indices could be, or said differently, index lookup could be that, but it's an index lookup. It's really just for, it's specific to that, and it's different. It's operating differently, and I think only here it looks so similar because it kind of is. Down here it's similar but also different, the logic, even though I could imagine also swapping loose object databases. I could imagine that. You know, now that you say it, essentially, yes, these loops, they're kind of the same. Let's see if there's something different. So here, there's a lot of difference. So all the pack management, blah, blah, blah. See, so here it's not the same at all.
Yeah.
And the other things, they're pack related, so it doesn't apply. So yes, you're right. In two cases, I think it looks very similar. It is similar. It could be the same, but it's something you don't actually, you don't really usually do this in Rust because it costs you, having a trait for this, and then what's the value just to save 4 lines of code? It's no.
Exactly. That's just in other programming languages, you just throw everything into a list or into an array and then just check if the function exists.
Yes, true.
but yeah, that's not allowed here.
Everything is an object and hash map. Everything is a hash map. Then you can do that, yeah. Not here. Cool, but another few refactorings also happened, so that's pretty cool. Yeah, interesting. I actually, that sucks. I forgot to update to actually commit this. Git diff. Okay. Now refactor. Is this the right? Is this the right ID? I think not. 298 it should be. 298. Oh, I copy my passphrase.
The clipboard.
Yes. Okay, fine. It's okay. It's just one line that was changed. I can redo that. But now, yeah, that's gone. That change is gone. It was never in Git, so no way to retrieve something. It's okay. I was aware that this could go wrong, and I risked it nonetheless. Okay, cool. Then I think next up is the short ID, which lives on the handle as well, interestingly enough. So yeah, we can just stay in this impl block and sketch the API, I guess. Oh yeah, by the way, sorry, I forgot one thing. Where are the tests for that? That's not the test. Here, I think here's the test. Lookup prefix. Yeah, I forgot one thing, which is we do have tests for lookup prefix to work, but we don't have any assertions on how the object database itself is working. In the sense of, it's lazy, are we sure it actually loaded all the packs that there are? And you can check that, and you should. Here.
The metrics, yeah.
Metrics. And here, returns none for prefixes without a match. And here we could say assert all indices loaded. This is something we need. Takes like 2 seconds to create this, but it's faster than than if I would have done it. So that's still okay. Think about it. It takes super long for a computer, at least, to do this kind of stuff. At least when implemented in Java, or on the JVM, let's say. But it's still faster than a human, much faster, I guess. So it's a value proposition. And
absolutely.
It's, yeah, if you see it like this, well, it's interesting. All right, there's a handle. And let's do it like this. I'm always a bit hesitant to create new users. Do I now have my, no. As always, I lose my clipboard, that's what I do. Okay, handle store ref metrics. Is this needed, or can I do this as well? No. Yeah, so each handle, there's this shared store, and that shared store is the thing that gets pounded by all the threads when you want to load a new index or something. That's the shared state that has to be thread safe, and that has to be fast while basically lock free. That's the point. In order to actually let the threads scale nicely, even though, because everything is cached in these handles, it doesn't even have to be so super fast. I think it would even be okay-ish fast if it was just one lock that locks the store. But I didn't ever try that. But that might be something to eventually explore. If there are bugs related to concurrency that affect the correctness of the implementation, there won't be undefined behavior here, but correctness issues could still occur. Then it's clear that maybe there's just one or two locks here, and that will then be it, instead of having a more complicated system as this is the case now. But anyway, independently of that, let's check what the metrics actually are to see what the value should be. So that fails.
Yeah, didn't we change the number of like indices because we duplicated we created the multi-pack index as well?
Yes. Okay, let's go through these numbers. The actual is 2 and 30 and 1. Okay. The whole store, no, all indices are loaded. All indices must be loaded to sure, must be searched, and loaded. Must be loaded and searched to assure unambiguous object IDs. Okay. So does it work now? And then we go through the individual values. Yes, that's the numbers. Handles, how many handles are currently known or using that store? This is something that it uses to understand to what extent it can forget about open indices or packs. But we can discuss that, or we don't have to learn everything about that now. But this is why it even tracks this, otherwise we wouldn't have to. Num refreshes, that's a number I could imagine will be quite different depending on the test, but we will see. Right now it refreshes twice, once when it starts, because it has to know what's there, and then one more time when it looks up the one prefix and just checks it and just refreshes disk to really be sure that nothing changed in the meantime, so that prefix really doesn't exist. This is why there's 2. Open reachable indices and known reachable indices. 2. Why 2? So we have 3 pack indices originally, right? And how do we get the number 2 now? Like the multi-pack, how many indices are in that multi-pack?
I think we had 2, right? We had
yeah. So 2 become 1.
Oh, and then there's one
left.
Pack index file. Okay.
This is why 2 is the right number.
I see.
Open reachable indices and known reachable indices. The difference is they're known right off the bat. This is the standard state that we know that they exist, that we can load them. But this means they're actually open right now. They're memory mapped. So somebody searched them, for example. And this is something we want here.
But this is still a bit confusing because we should have essentially 4, right? Because we have 1 multi-pack index and we have 3 pack files. So it has to scan all of them to know that there is overlap, right?
Yeah, but it does. But where are the objects? Like the knowledge about objects and whether they're present or not, it's in the indices. The packs have the data. So the multi-pack index, it's literally superimposing itself on top of the indices that it replaces.
Mm-hmm.
And it doesn't really replace them, it's just another way of accessing that data. Because these indices that it was made of, they are not deleted, they're staying there. So the multi-pack index is always something you can delete, and your repository will still work. It's just an accelerator.
Mm-hmm.
And yeah, this is why that seems to be correct. Open reachable packs, 0, also correct, because we didn't access any data of any object, so
right. Mm-hmm.
Nothing is open. Known packs, 3, because we have 3 indices, 2 indices, but 3 packs in total. The multi-pack knows 2 packs. The multi-pack index knows 2 packs because we created it from 2 indices, and the remaining single index has its single pack. Yeah, and these slots, that's also interesting. Slots. So there are 32 slots in total in this particular map, and the amount of slots is fixed. That cannot grow. So after you create or instantiate that object database, or when you create it, you have to find a number of slots that you want. And 32 is a good number that should work for most object databases out there, but not for all, mind you. If you have 60 indices, for example, this will not be enough, because each index costs you 1 slot.
Mm-hmm.
And this is why, yeah, known reachable indices plus unused slots, that's the total amount of slots that you have in your object database. That's why I know it's 32. And this slot map is the thing that enables the snapshotting mechanism, It's also something that Git Oxide works hard to not let you know about, in the sense of it automatically detects how many packs there are, and then if it's more than 32, which is the minimum, it will automatically take more. But that's an option you have. Like if you're running on the server, you can say, I maintain my object databases, this will never be more than X. Then you can just say, come up with 32, come up with 40, come up with 16. And the smaller this thing is, potentially, you might save a few cycles there, but probably it doesn't really matter with these sizes anyway, because that's pretty small. And the default though is to basically have an extra access. First, it checks disk to know where the packs are and how many packs there are, or indices, and then it sets the number accordingly, and you will always have enough when you start or instantiate the object database. Whose object database is 1, and there's no garbage. Unreachable packs 0, unreachable indices 0.
How can there be more than one loose database? Is it just the amount of folders, or just different locations?
It would literally be different locations, because that's the Git alternates here. You have this Git alternates file. Where is it? I think it's an info alternate, maybe. You have to create the files. It doesn't exist by default. But if it does exist, you can point to some other object database like this, I think.
Okay.
And this is how you have multiple loose object databases. You have multiple sources for packs as well.
Mm-hmm.
And yeah, you usually use this to have cheap clones. You can make a clone on a local, you can say clone, but only reference that original database. And then your clone will have a full working tree, but the objects will be pulled from that original.
The other location.
Yes. Mm-hmm. And this works because I mean, this works because of the alternates file here. It just links multiple databases together. And if you create new objects, these new objects will be written into your own object database. And this is how you have a layering of object databases essentially, or of databases in general. And that's pretty cool, but I think it does have some downsides. So ultimately, I think I don't know who uses this still. This was made for servers originally, but is not used there anymore. No, it's monorepos there, I think. What do I know? As long as you don't run your own server, you probably don't really know. Okay, it's all theory. Now let's try this for another one, for another test, and then I think we are good. Like what are the values essentially? Yeah? Let's learn about the values and just vet them to understand what's going on. The next one, return some error for prefixes with more than one match. Okay. Yeah, that's going to be interesting. Will it have to load all the packs or not?
No, we bail out early, right?
Yeah, but it might, I don't know. It depends on where it finds the duplicate.
Yes.
And I don't know where that is. Okay. Num refreshes 1. So it looks like that's something we want to have as a parameter here. Num refreshes. And see, this is why I use IntelliJ. No, I might dislike the tech stack as much as I want, but that's the thing it does that no other IDE does.
Yeah, true.
That well, yet. That's the cool thing. Visual Studio Code and the language server, the Rust language server team is really, they're on fire. Rust Analyzer, Visual Studio Code integration, and they add all this kind of stuff as well, but with Rust power. And then, of course, I don't think they have a chance to compete then in terms of speed and performance, and probably they can also develop faster then and be more tightly integrated with the compiler and just know more about the code. And this is why I think ultimately Visual Studio Code and the language server will win. But Fleet does also have language server support, so they can just use the best of all worlds, so to say. So it's not that JetBrains is out of business. At some point, they stay relevant. And look at this here. It automatically adjusted all call sites to have that additional parameter. So here I can now go down to 1, and that should make my test screen. Yeah. Oh, what? Yeah, open reachable indices. Right. That's the thing that explains the refreshes, because we find the duplication already in the first index. And this is why I probably have to make this one as well. Okay, that's 2, and that's also 1. Nice. And now for the last one. Let's see what it says.
It should be 2 again, right?
Good point. 2. No, wait, I don't know how, the first one is num refreshes. I don't know how many. I think it's way more, because for each prefix it will have a refresh here. I think.
Oh, okay.
But it's 2 here, yeah. And that's the thing, like this is why I wanted this test, because now we see that the current implementation actually has a performance issue. Like I said initially, if you don't configure your handle correctly. And we will just do that and see how that works, you know, because that should work. Let's see what the values is. There, 147. 147 objects. I would like to bring that down to 1. Just 1 refresh, the first one, and then never again. Because we know, we are in a situation where we know this is read-only, nobody will change our database. That's okay. And it's literally true, by the way. Like this iterator, in the moment we use it, it will operate on a snapshot of the object database. And even if something changes there, it will not see these changes. And that's the benefit of this system, that you can freeze the state in memory just by keeping shared ownership of open memory maps to your indices and your instances of your object databases, which are really just path on disk. And that allows you to iterate over all objects as they have been on that at that point in time. And another thread could come and could trigger a refresh, and that refresh could find new stuff on disk, or things removed, things added, whatever, which changes the state, but that will not affect this iteration here. And this is how the view is always consistent for each operation, which includes things like iteration where there is multiple things going on. So the whole working set is frozen. And that's why this object database system is so cool with the snapshotting. And it's cool that it's actually fast, so that you don't need locks most of the time. And it's neat. Copy on write, things like that, shared ownership, it's nice. I like it. It takes 3 times as long to write this thing because of all the concurrency that you have to keep in mind at all times. But it's worth it. Okay, now handle, please, can you not refresh anymore? That would be nice, wouldn't it be? I'd like that. Okay. Okay, for the lazy people that don't want to assign this, but look, now I would be tempted to even do it like this, huh? Then it reads nice. Handle refresh, never. Even though it's more like store refresh, or refresh from disk or something like that. But yeah, this could be better now. Refresh mode, never. Okay. And look, the test actually passes. So now that we forbade it to ever refresh, it just uses the initial set of files it saw and bails out without refreshing, and we save a lot of time here.
Yeah, and this will be a configuration thing, like just depending on how you use this,
yes.
You can be efficient or not.
Yes, and the caller knows that, right? This is why the caller configures it. And it's per handle and not per store. So that's also something very cool, that all this works on per call site level. And what's also cool, which is super non-obvious here, I think, is, yeah, see, so that's not a handle, actually. Wait, that's interesting. Oh yeah, get ODB handle, but the handle is actually this. So it's a bit more complex to type, but it's a store handle that has a store inside with shared ownership, own shared, right? But it's surrounded by a cache, kind of literally, like you wrap a cache around it. So now everything that you do with the handle is going through a cache.
Mm-hmm.
And that cache also has configuration. And that configuration, the effectiveness of the cache, so to say, often depends on you knowing what you're doing. And you experiment with good cache sizes and with good cache types, and then you set it up or not. And by default, there is no cache at all. But for some algorithm, you want an object cache. So whole objects are cached by their ID. For some accesses, you want a pack cache just for a general speed up, so to say. But you know best. And sometimes, you only get, like, you get a handle to some repository or the repository itself. But since creating handles is so cheap, like if you would have a read-only handle which somebody passes to you, like I had exactly that case in Cargo Smart Release, where there was only a read-only handle available, but I wanted to change the configuration of the cache. So what do? You clone it, make it your own, because clones are so cheap, and now you have a local cache just for your operation that greatly accelerates that operation by maybe 4x, 5x, 6x in some cases. And then once you're done with it, you throw away the handle and the cache goes away with it and the memory that was used. And that's exactly the behavior that you want. And that's exactly the capability that you want. And that's the cool, it's not bragging what I'm doing. It's just being amazed that this emerged after so many attempts to do it. It's more like it didn't happen the first time around, but over time it emerged and it became clear what it had to be to be that capable, and you just benefit. And that's cool. Once it really matches, it just falls into place and it sticks and it feels good. And that's just, this refresh mode, I can't see it.
Looks really nice. Yeah, like you configure your access essentially before you do it, just to make it do the thing that you want and be efficient with it.
Yes, and it makes so much sense. But of course, I didn't figure that one out the first time. Like, like when do I ever figure stuff out the first time? I don't know. Pretty rare.
When does anyone?
Yes. I learn by mistakes. But I learn, so that's a good thing. Often, not always. So, cool. That works. And it looks much better. There was really a bunch of refactoring here. And that's now in a state where I say, yes, we can move on to the next thing. But probably that is for tomorrow. 40 minutes in, we wouldn't start a new thing, I think. Cool.
Good.
Then thanks a lot for watching and see you next time.
Bye-bye.